Okay, we're looking at question 5 now, which is very relevant given current circumstances. So a test is developed to determine whether or not someone has got a disease which is known to be present in 3% of the population. And given a person has the disease, the test is positive with a probability of 98%. So the way this question set out suggests to me that I should be using a tree diagram with whether or not they've got the disease on the first set of branches and whether or not they test positive on the second, because I've got my conditional probabilities which I really want to have on my second branch. So what I'm going to do, part A, we're going to say these are the people who have the disease, these are the people who don't have the disease. These are the people who've got the disease who then test positive. These are the people who've got the disease who don't test positive. These are the people who don't have the disease who do test positive. These are the people who don't have the disease who don't test positive. And if we think, having the disease, testing positive, this is where we want to end up. Not having the disease, not testing positive, this is where we want to end up. Having the disease and testing negative, well, that's called a false negative. We don't want to be there. Not having the disease and testing positive is called a false positive, and we also don't want to end up there. So we know the disease is present in 3% of the population, so we can say that the chance of having the disease is 0.03. That means the chance of not having the disease is 0.97. For the people who have the disease, they test positive with probability of 98%, so 0.98, 0.02. If they don't have the disease, they test positive with probability of 5%, 0.05, and 0.95. And what's going to be interesting in this example is that 5% of a false positive is quite high, and we start thinking that the number of people who test positive out of here might actually be just as great or greater than the number of people who test positive here. So you might actually find that even if you test positive, your chances still are that you don't have the disease rather than that you do. But we'll have a look at that in later questions. So find the probability. For part B, we need to find the probability that somebody tests positive. So probability of testing positive is going to be that they end up here. So it's the probability of D intersection P plus the probability of D dash intersection P. D intersection P is 0.03 times 0.98. D dash intersection P is 0.97 times 0.05. That's going to give me an answer of 0.0779. So just under 8% of the population is going to be testing positive for this disease. Part C is asking us to do a conditional probability calculation. So it's saying a person who tested positive is selected. So we can say this is person who tested positive is selective. So we know that this is going to be given that they're positive. Find the probability they do not have the disease. So this is not having the disease given they tested positive. Okay, well that's going to be the probability that they tested for the disease, that they didn't have the disease and they tested positive, divided by the probability that they tested positive. Well, D dash intersection P was our 0.97 times 0.05. The probability of testing positive, well, we already worked it out in part B as 0.0779. That's going to give me 0.0485 divided by 0.0779. And that gives me an answer of 0.623. Now this this is really important, and part D asks us to interpret it. Even though they tested positive, the chances were still that they didn't have the disease. So this test is ineffective as the majority of those who test positive do not have the disease.